So we want to talk about Good Willie Jones. Which says, I'll state it very vaguely because we'll need to define everything, but it's going to say that if I have some space, so X will be any space, some topological space, some homotype type, and I have the mapping space from the circle to X, so the free loop space. And the circle acts on here just by rotating the source. And so it acts on the homology. And this will be equivalent to Hochschild homology of, let me say it like this, infinity local systems. So I'll say what this means, and then once I've said what it means, I'm going to drop the infinity. But it's kind of like a derived category of local systems in a precise sense. And over here, I have the cone B operator, which is the generator of a circle action, of the homology of the circle on the Hochschild complex. So the theorem is that this is a circle equivariant equivalence, and it also works at the chain level. So this is what the theorem roughly says. And so I'm going to start by kind of telling you how to work with this category. And I'll also give a kind of more algebraic description of it, and I'll also give an alternative approach to talking about Hochschild homology, which will give us a fairly easy proof of this theorem if you believe that a lot of diagrams commute. Okay, so the first bit, kind of part 0, is about local systems. And usually, I mean, classically, when you talk about local systems, you have some space, you have some point, you have the fundamental group at that point. And let's suppose this is connected. Otherwise, I have to consider many points, one for each connected component. And then there's an equivalence between representations of pi1 of any rank. I could say modules. I don't have to do field coefficients. So pi1 modules, and locally constant sheaves. So I can do this with any coefficients, but let's suppose we did it over the integers. Then this would be locally constant sheaves of abelian groups. If I had some ground ring, commutative ring K, it would be K modules.
Is it like when in algebraic geometry we take Poisson sheaves and they come from modules of the global section?
Kind of. Except that
What's one Z?
I just mean with, let me say it like this. Take the group algebra over Z.
Yeah, sure.
Okay, and then I could put any other commutative ring here too. And the,
Wait, here's a question which I've asked myself today, and I realized that I don't have the answer. Well, it's a question for everyone. Suppose we have a map from X to Y, finite subsectional complexes, which induces an isomorphism of all without a cohomologizing isomorphism with coefficients in all local systems. abelian groups. Is it true that the map is a homotopy equivalence?
By all coefficient systems,
Not necessarily a finite track.
I've also asked myself this question, and I'm not. I think if you know, I think you also have. It's not enough. I think you need to know this also for pi 1.
That's part of the question. Does
Well, for example, I think I know how to answer this kind of question, but I don't want to get sidetracked now. This is a good question. I've also thought about this, and I thought I had an answer at some point.
Okay, let's not get distracted. But do you think the answer is yes, or the answer is no?
I want to be a little careful.
Okay,
Yeah, okay. So I think probably not. I think not. Okay. Okay, so right, so this is equivalence, and how does it go? Given a locally constant sheaf, I take the stock at a point, so that gives me some abelian group in the stock, and given a loop around, a little neighborhood of the base point, I can trivialize. I can make the constant sheaf constant, so I can transport a vector from that fiber to a nearby fiber, and then I start trivializing it on neighborhoods of points along the path, and as I come back, I don't necessarily come back to where I started. Well, you see this in complex analysis as well when you do analytic continuation. So it turns out that this transport along a loop only depends on the homotopy class, and this defines an action of pi 1 on the fiber. And you can check that, well, you can explicitly construct an inverse to going from locally constant sheaves of abelian groups to pi 1 modules. And the inverse is constructed similarly to how you go from spaces with action of pi 1 to covering spaces. We need more than this. So note that this category doesn't know very much about your space. So pi 1 could be trivial. And then this category is just abelian groups. So I'm going to call this loc heart of X. I'm going to call this, because it's an abelian thing. It's the heart of some T structure. So loc heart is then just abelian groups. Representations of the trivial group. And however, we would like X of the constant sheaf to itself. We would like that to be cohomology of X. So we would like some category in which the X are giving cohomology with coefficients. More generally, if I have a system here, I would like this, and this is cohomology with coefficients. So this is not true in general, for instance, in this example. And so we need to create a bigger category of local systems in which these are the correct X.
But wait, we can take X in the category of
So the question is, in which category should I take X so that this is true?
because well, the category of local systems is not well, it is abelian.
But it won't, if you take the Uneta X, it in general won't give the right answer.
Yes, on the other hand, if we take sheaves with the constructible cohomology.
Yeah, so I'm going to give 2-3 descriptions of it. Okay, so one solution. One solution is to consider the derived category of all sheaves. So this is kind of derived category of all complexes of sheaves. And then inside of there, we could consider, well, like I said, we could consider constructible, but I don't care about that today. So I could just consider the full subcategory of complexes such that each cohomology sheaf is locally constant. Okay, so that's a good category, and it of course has inside of it this heart, and in fact this is the heart of the obvious T structure on here. However, this category is not in general the derived category of the heart.
Oh, there's what structure?
T structure. So when you have complexes, you can truncate them.
Yes, but why is this enough? Again, if the space is interconnected, then basically you require that all homology sheaves are constant.
Yes. But then there are non-trivial extensions between them, and so you get some non-constant things in this category. So there is such a category. And if you believe that sheaf cohomology computes usual cohomology, then this will work. And let me give a warning and then a kind of solution to the warning. So warning is that well, there's a big abelian category of sheaves concentrated in degree 0, which are locally constant. It's an abelian category. It can form as a derived category. And in general, this is not the same as the thing I just defined. Even though this is a full subcategory there. So the X are different in general. So the problem, so this is basically unless what? Let me give you the correct statement. So this would be what? This would be D of the group algebra. Okay. And the reason this is not an equivalence in general is that it's not quite right to put the group algebra here. There's something a little smarter to put here, which is a kind of derived group algebra. So you can fix this. By introducing a kind of derived group algebra and considering DG modules over that. And then this will be an equivalence. So let me say what I mean by this derived group algebra. But to motivate it, I want to recall a theorem of, I think, Stashev. I think this is from Stashev's thesis, although I've never read it. But people usually attribute this to Stashev. So consider pointed connected spaces as a category. Those pointed maps and and here consider topological groups. Given a topological group, I can form its classifying space. That comes with the preferred base point. So that gives me my pointed connected space. And the claim is that, well, this is not quite an equivalence, but it's equivalence in a homotopical sense. So, so this is an equivalence. Is well, nowadays people would say an equivalence of infinity categories, meaning if you take the obvious weak equivalences on either side, then it induces an equivalence between the smart localizations with respect to those.
And is there an error in algebra?
There is, kind of. So the inverse is x with a point and goes to base loops on x. And now you have a little bit of a problem. You want to make this into a topological group. Okay, so so the problem is that concatenation of loops is not quite, it's not associative, it's associative up to homotopy. And you have to keep track of this homotopy, otherwise you lose information. So there are different ways to deal with this. So one way is to introduce a notion of A infinity space and A infinity group, which is why this has Stashev's name on it. So I think he invented A infinity spaces. So you could do a kind of up to coherent homotopy version of topological groups. So kind of replace this, resolve this category by another equivalent category. And then figure out a way to make this into an A infinity group. Another way to do it is to find a more rigid model. So, solution to, there are various solutions to this problem. One is use A infinity groups. Another is use more loops. So these are some kind of parameterized loops. It'll give the same homotopy type, but it'll give a strictly associative multiplication. And a third way to do it is to use the Kahn loop group. So replace pointed connected spaces with pointed simplicial sets. Replace topological groups with simplicial groups, and then you can make this more rigid. So you can write the functors down in both directions and show that there's equivalent equivalence. So you can use the Kahn loop group. So I think probably they do this in the book of Gerst and Jardine. I think they probably proved this theorem in the simplicial setting. So one way or the other, either using some fancy infinity machinery or zigzags of equivalent equivalences with different models, you can prove this theorem. So let me give this a name. I think topologists call it looping delooping. So this one is looping, and then the classifying space gets called delooping. And this kind of procedure of looping and delooping appears also in algebra, especially in Gazelle duality. Every time you see a shift by 1 or minus 1 in some complex, this is usually what's going on. Some form of this. Okay. Right. So if we're trying to study local systems on a space, say it's connected, then we could think of that space via this equivalence as being equivalent to a classifying space of some group. So X is weakly equivalent to the classifying space of some group, which I'll call omega X, where you need to interpret this in whatever way makes you feel comfortable, one of these ways. And we want to study local systems on this. So and this should be suggestive, kind of in if you're familiar with stacks, this can also be thought of as a quotient of a point by this group. And then maybe you're familiar with computing some kind of sheaves on this in terms of representations of that group. So we'd like to study this as kind of representations of this base loop group. And notice what pi 0 of this thing is. This is just pi 1 of the original space at the base point. Okay. So this is going to be a generalization of pi 1 representations that takes into account higher homotopy groups of this loop group. And so the reason this was failing in general is, so let me continue saying something about the warning. Right, so this game will work. So if this is discrete, this is exactly the case when this thing is homotopy discrete. Then this will, we didn't need the warning. So d of pi 1 will be equivalent to this infinity local systems. And this is when, happens if and only this. So this is discrete precisely when, what is it saying? X is k pi 1. We're saying it's the classifying space of a discrete group, at least up to homotopy. So away from the k pi 1 case, away from Eilenberg-MacLane spaces, we have to worry about this issue. And then the theorem, I don't know, I don't even think it needs a name. It seems topologists all know this. This category of local systems, this infinity local systems, this is, it's not pi 1 representations in general, it's DG modules over. So I have a topological group, which is these base loops. Given a topological group, I can take its chains. And by pushing forward along the multiplication and using, I don't know, whatever the map is between chains of a product and tensor product of chains, this becomes a DG algebra. It's called the Pontryagin product. And I can take DG modules over it. Okay, so there's an equivalence like this of DG categories. And so you can think of this thing as a kind of derived group algebra, which fixed the failure of this to be an equivalence.
So is this the definition of the left-hand side?
I could take as the definition the full subcategory of sheaves, which with locally constant cohomology sheaves. That's one place I could start as the definition on the left-hand side, and then I could prove this theorem.
Okay.
Mm-hmm. There are purely homotopical definitions of the left-hand side as well, and under which you can also prove this theorem. So there are actually kind of three categories. One is this full subcategory of all sheaves. One is something defined purely homotopically, which I haven't defined yet. And the third is these DG modules. And you can, compare all of them.
Okay. And it turns out the homotopic categories are the same.
Yes.
What exactly is the same?
It's an equivalent, a quasi-equivalence of DG categories. So this is of DG categories, meaning it's not just the homotopic categories, but the mapping complexes match up.
The maps of the homoses are quasi-isomorphic.
Yeah. So in particular, let's write a corollary of this then. Corollaries of this. In order to make sense of the corollaries, maybe you need to work out a little more of the functoriality, but it will follow from this that cohomology, so let's give the functor a name maybe. Let's call it maybe M for module, sub whatever the name of the sheaf is. So let's say cohomology of X with coefficients in one of these complexes with locally constant cohomology under this equivalence is, let me say chains. This is cochains. This is R hom over this DG algebra from the constant sheaf to whatever the corresponding, well, let's say the trivial module. So there's just like for the group algebra, in degree 0, H0 is the group algebra pi1, there's an augmentation. So this is cohomology in the sense of an augmented algebra with coefficients in the module that corresponds to the sheaf. Okay? And similarly for homology, there's also twisted homology. That's something that makes sense. And that will be the derived tensor product. It will be the co-invariance. So this would be okay.
What is MF?
I'm calling like F goes to MF. I just wanted some kind of.
So F is a sheaf.
F is a sheaf. M is the functor that takes F to MF.
Did we construct it?
No, it's kind of buried in the proof of this theorem. And we're never going to use it. I just wanted to. The reason I'm introducing this is because in the original paper of Goodwillie and Jones, they talk about this DG algebra explicitly, rather than this category. And I actually prefer to talk about this category for the proof I'm going to present. But I wanted to give this as a bridge between something that looks close to what you classically think of as local systems, and also something that appears in the original papers. So you can read more about this formalism about this category and these calculations. There was a student of Cohen, Ralph Cohen, who wrote a thesis about this kind of stuff, and also does some calculations in string topology. So in Eric Malm's thesis, there's more about the DG modules over this and relation to string topology. It's a nice thesis. It's easy to read. Everything's done pretty much from scratch.
Sorry, what do you mean corollary by the left-hand side? What is C star?
Cochains of X with coefficients in this local system, so twisted cochains.
Yeah, you mean it's applicable only for F being a local system, not an object in derived category?
No, F is here. It's a infinity local system, so it's a complex.
Yeah, it's complex, but
It's not a
condition on.
That's right. So if I had some sheaf which was not local, if I had a complex of sheaves which was not locally constant in this sense, then it has nothing to do with this algebra. Notice that this right-hand side, it's obvious from this point of view that the right-hand side only depends on the homotopy type of X. Where when I define this as a subcategory of sheaves, it wasn't obvious that it was only dependent on the homotopy type of X, because the category of all sheaves depends on the topological space.
So it's important that we take sheaves with constant homology.
In order to get something that's homotopy invariant. Yeah.
And it is homotopy invariant.
It is. So if you believe this theorem, then it's clearly homotopy invariant.
So right-hand side is.
Yeah. However, there's a third approach, which is purely homotopy theoretic. Doesn't you? So I don't want to get into it, but it's you can think of a homotopy type as an infinity groupoid, where the points and the objects are the points, the one morphisms are the paths, the two morphisms are homotopies between paths, and so on. And so an infinity groupoid is a special kind of infinity category, and you can study functors from it, infinity functors from it, to the category of, I don't know, like DG modules, say, complexes of abelian groups. That forms a category. You can think of it as like representations of the infinity groupoid. And that's a purely homotopical way to talk about this category. It's also equivalent to this. So in Lurie's higher algebra book, he doesn't talk about this, but he does talk about the thing I just said, representations of the infinity groupoid, and the subcategory of sheaves with locally constant homology. And he proves that those are equivalent.
And to construct the infinity groupoid, we could do, which is, we don't need topological spaces, we can do like some other way.
I mean, the way the theory of infinity categories is set up, infinity groupoids are the same thing as homotopy types. I mean, that's like in any theory of, any model of infinity categories you construct, this is the first thing you check. It's called the homotopy hypothesis. It's like desideratum number 0 for a theory of infinity categories.
Sorry, I asking again. I don't understand corollary at all. I don't understand what both parts are.
Okay. So let me try to rewrite it. Okay, so let me introduce more notation. So first of all, this DG algebra has an augmentation, which is just like push forward to point. to the trivial group. Okay? And so I can consider this as a DG module over this by restriction. So over here, I mean that trivial DG module. If this were just a usual group algebra, this would be the trivial representation of that group. So this would be like group cohomology.
So it's actually just X. It's not anything to do with some abstract complex, because they have a left-hand side, a right-hand side not have distinct origin. So it's just X. It's nothing else.
It's more than X'd, right? Because, I mean, I cannot say with integral coefficients, I cannot reconstruct a complex just by knowing its cohomology groups. I need the extension data.
Okay, this is a complex of what?
This, it's a complex of abelian groups.
Okay.
And what is this one? So what is this? This is Arham in sheaves. Remember, it's a full subcategory of derived category of sheaves from the constant sheaf to F. And I'm claiming that under this equivalence, that this constant sheaf maps to this trivial module. So part of the assertion is that the constant sheaf maps the trivial module. And well, this was just notation. It's wherever the sheaf F maps to. I called it MF because M is a module. And then something similar for Tor. This is like group cohomology. If I think of this as just a group algebra, this would be group cohomology with coefficients in this module. And this would be, this Tor would be group homology with coefficients in this module. And the left-hand side is homology of X with coefficients in F. So what is that?
F is again
A local system.
F is a local system or a sheaf with a complex of sheaves with constant homology.
And one can define homology with twisted coefficients.
Well, actually, if X is less than compact, then one can define homology with coefficients in an arbitrary sheaf. Let's say stratify it in a sensible way. What one needs to do is take the dualizing sheaf and tensor it and invert the degree.
Okay. Does this give homology or Borel-Moore homology?
The Borel-Moore homology. If you want homology, take with compact support.
Mm-hmm. Right. Here, what I would say is that this category of infinity local systems has more functoriality than the usual category of sheaves. There's pullback, and that's the same as it is on sheaves. And there's push forward, which is like when you push forward to a point, you take cohomology. But it turns out pullback doesn't just have a right adjoint, it also has a left adjoint when restricted to this category, and that's homology. Okay, right. So anyway, the point of this is a digression, but the point is just to show that there is some generalization of the usual abelian story about local systems where you can describe it either kind of topologically or describe it more algebraically. And this more algebraic description is the one that Goodwillie and Jones prefer. I'm going to prefer this one. Okay, so now I'm going to want to get back to this Goodwillie-Jones theorem. We want to say that the homology or chains of a free loop space is going to be Hochschild homology of something. You could take it to be Hochschild homology of this algebra, and that's what Goodwillie-Jones do. Or you can figure out how to define Hochschild homology of a category independent of an algebra. And for the proof I want to give, that will be better. It will be kind of more invariant. So I need to explain how to think of Hochschild homology in this way. Okay. So this is kind of part 0. Part 1 is Hochschild homology of DG categories. I'm going to write big DG. So these are big categories because I have complexes maybe infinite in both directions. And this is going to be via formalism of traces. Okay. So that needs motivation as well. So now for something very elementary. So recall, suppose V is a finite dimensional vector space, or maybe a finite rank projective module over some commutative ring. But let's say vector space for simplicity. And suppose I have an endomorphism. This is an endomorphism. Then I could compute its trace by choosing a basis, writing down a matrix, and summing up the diagonal. But there's an invariant way to express it, which is very handy. So we can compute trace as the composite Okay, so let's see. I'm going to consider V tensor the dual. To get this right. Well, okay, I'm going to skip one little step because it's not important for what I want to say. So consider V dual tensor V. I could put the endomorphism on the second factor. Here, I have evaluation. I have a linear functional, I evaluate it on a vector. I get an element on my ground field. And here, I can identify this with endomorphisms of V in the usual way. And there's the unit in there. 1 goes to id V. Okay? And so everything I've written down is defined in a basis-independent way. But if you go ahead and choose a basis and follow the composite through, you'll find the trace in the sense of summing along the diagonal. And what's good about this is it allows you to define trace in any category which has a tensor product and where the objects you're considering have a dual in some sense.
What's the first arrow from A to and V?
1 goes to the identity. And so in a basis, it would be like the sum of the dual basis tensor the basis. So 1's a pairing, and then the fact that the pairing is non-degenerate means there's this co-pairing. Okay. So this generalizes. To traces of endomorphisms of dualizable objects in symmetric monoidal categories. So we had symmetric monoidal categories when we were talking about operads. I have some category. Comes with a notion of tensor product, and it has a unit for the tensor product. And it's symmetric in the sense there's a natural way to identify x tensor y with y tensor x, which satisfies all of the identities you'd like it to. And tensoring with one on either side is naturally does nothing. Okay, so we say definition, an object in here is dualizable if there exists another object called x check and maps x check tensor x mapping to the unit of your symmetric monoidal category. So that one's called evaluation on x. And there should also be another one. And actually, I don't know how important this is or not. Usually the way people write it is the co-evaluation takes values in x tensor x check, like that. So I could have rewritten this as like v tensor v, and I could have put in the twist somewhere in here. Such that, so this is supposed to be like a pairing. It's supposed to be the co-pairing, like sending one to the identity. They have to satisfy a kind of non-degeneracy property with respect to each other. Let's see if I can write it down. So such that, let's see if I get this right. So for all y, I think it's for all y, yes. For all y, we should have the following. So let me get this right. Do I need it for all y or just for x?
Just for x.
Yeah, okay. Then I think something follows for all y. Okay, so look at these two things. This one, I can tensor on the left with x. And I'll get x check x. This one, I could tensor on the right. And I'll get x check x. Okay? So such that the composite,
I think we're supposed to have a break.
okay. So let me finish this definition and give the definition of trace, and then we'll take a break. So the composite x, which is what? I said tensor this on the right. So this will be 1 tensor x. I'm tensoring the co-evaluation on the right. So I'll do nothing on the right-hand factor. So this will be x check x. And then on the other side, I'll have id on this factor, evaluation. Okay, so that will give me x and 1, which, since the unit is x. So this composite should be the identity. Okay, so that's the condition on x. And if you try this for the usual pairing between a dual vector, a finite dimensional vector space and its dual, it's easy to check that this is the identity. So exercise. If C is the category of vector spaces with the usual tensor product, and K is the unit, then V is dualizable in this sense if and only if it's finite dimensional. More generally, if K is a commutative ring, a module will be dualizable if and only if it's projective of a finite rank.
Does it follow from this axiom that the dual is half to 1?
Yes and no. What's that?
Do we need another axiom?
Yeah, you need more because in general, the way I said it, there might not be an internal hum. So, yeah, but I mean, if you have an internal hum, then yes. And even more, like internal hum from a dualizable object into any object will be the dual of the dualizable object tensor, the target. So you can have like an infinite dimensional target for a vector space. Okay, so the exercise. First, vect V is dualizable if and only if it's finite dimensional. And 2, if V is finite dimensional and W is arbitrary, then the natural map from V dual tensor W to hum VW is an isomorphism. And you can generalize this. You can generalize this kind of statement if you have an internal hum. Mm-hmm.
I have a purely formal question. Does dualizability is equivalent to saying that a tensor ring with x as a functor has no which is which happens to be a tensor ring.
Just a sec. So if we were working in a module category, then tensoring would always have a right adjoint which is given by hum. But then you could ask, when is that hum also given by a tensor product? And then it turns out to be true under like over a commutative ring and so on, that yes, it's equivalent that the right adjoint, which is given by the hum, should also preserve colimits and therefore being given by a tensor product. And that tensor product will be the dual module. So that's true. What's going on there is that there's a tensor way to characterize the dualizable objects, and there's a hum way. The hum way is to say hum out of it preserves all direct sums of DG modules. So these are what are called compact objects. Okay, now let me just give the definition of trace, and then we can take a break. So the trace, let me say, so definition. The trace of an endomorphism of a dualizable object. So let x be dualizable. Then with an endomorphism phi, then trace of phi is an endomorphism of 1 and it's given as a composite I take 1 x tensor x check, that's the co-evaluation, which exists because x is dualizable. Then I apply phi on one of the factors. Then I swap, because it's a symmetric monoidal category, and then I take evaluation. So that's a well-defined endomorphism of 1, and by definition, that's the trace. So let me stop there. Let's take a break.
Okay. How long do we need? Probably 10 minutes or so.
10 minutes is good, yeah. You can't turn this thing off, can you?
I can turn off the sound.
Okay, okay. I don't want to, but I should. There are many things in life that I don't want to do, but I should do. Once upon a time, people used to keep promises and have a list of duties that they tried to fulfill. But we've all become very degenerate since those days. Okay, so there's pullback and push forward. So these are in the derived sense. And in this local systems case, it turns out that this one has a left adjoint, which is called I lower shriek. And claim is that if I push forward just the constant sheaf on the point, so just z, that this is, so this is this is a comment for those for whom it makes sense. It's not necessary for the rest of what I want to say. This is a compact generator of the category of infinity local systems. And so the functor R-HOM out of it, well, that, and then the derived endomorphisms of this is equivalent as a DG algebra to this chains of the base loops. This is a kind of base change statement. And third, this equivalence is f goes to R-HOM out of this object. Okay, so that's what it is. And so insofar as you can explicitly describe this thing and find a resolution of it so you can compute R-HOM, you can make this functor explicit.
Yeah, it's exactly a construction I meant by something of geometric origin. So you really take a common model for loop space that take a contrastable space where it gets free.
Okay, right, so we had this notion of dualizable object in a symmetric monoidal category and trace of an endomorphism on a dualizable object. And we want to apply this to Hochschild homology. We want to define Hochschild homology as some kind of trace. And we want to also see that loop spaces are also a kind of trace. And then some compatibility between these will give this theorem of Goodwillian and Jones. But we need a kind of slightly fancier version of these theory of traces. So let me right. So the relevant setting, so these are two categorical traces. The two categorical part is just extra functoriality and extra structure, but the formula for the trace is exactly the same. So now the setting here is C, tensor, and 1. This is a symmetric monoidal two category. And so two categories, something with objects and morphisms, and two morphisms, which behaves like categories, functors, and natural transformations. And let me give two examples. So the example I'm interested in for Hochschild homology will be what's called big DG cat cont. Actually, I could probably even do better than that. Well, okay. So what are these? These are differential graded categories, C, which are presentable. Let me just call this. Maybe I'd call it D. This is a fancy C. This is D. That are presentable. So very roughly, these are things that look like localizations of categories of DG modules. So it's some kind of technical set theoretic condition. And so examples, all of the examples would be, this locoinfinity is an example. DGR modules over DG algebra is an example. The kind of categories like quasi-coherent unbounded derived category in algebraic geometry is an example. But there are other examples. So I could consider all sheaves on X. This is a kind of fancier example where you really need this notion of presentable. These ones, you can describe them in terms of small categories. This one, not so much. And there's a tensor product of such things. So, okay, so these are what the objects are, and the morphisms are, so I should say some more about what this means. So there's a technical set theoretic condition, and also it has all homotopy limits and colimits. And then the morphisms are required to, this is what cont means, it means continuous. The morphisms are continuous, meaning they preserve colimits. And so they have right adjoints, but the right adjoints kind of leave this category. The right adjoint itself is not necessarily continuous. So examples would be fact. Every continuous functor. So I'm just trying to give you a sense of what functors in this, what morphisms in this category look like. Every continuous functor from a category of DG modules to another category of DG modules. F is of the form given by tensoring with a bimodule. So this will be, if these are left R modules, it's of this form with P should be a SR bimodule. Okay. And what this P is just the image of F of R. So in this setting, the morphisms between this DG category and this DG category in this ambient thing of big DG categories, they're just bimodules. And the two morphisms are natural transformations, so DG natural transformations. And in this setting of, if I'm working with categories of DG modules, then the natural transformations are just given by maps between the bimodules. So this is the setting in which we want to work, and a very nice feature of whatever presentable means is that there's a tensor product of presentable categories. So there is a tensor product of presentable DG categories. Some people call this the Lurie tensor product, and there's a kind of abelian version of this, maybe due to Deligne originally, but in this kind of DG setting is due to Lurie. And so this is some symmetric monoidal 2 category, and we're going to be interested in the dualizable objects here and traces. Okay. Right.
Who is unitable object?
Yes. So I should fix a ground ring. I could, for instance, take the integers. And so then 1 in DG cat is supposed to be an object of the category. Objects are DG categories, so the unit has to be a DG category. It's DG Z modules. So in the second half of the talk, we're going to pretend to be cool kids, and I'm not going to write DG or derive functor and so on. Everything is just implicitly derived. So these are DG modules. And so the claim is, whatever this tensor product is, one property it has is tensoring with Z modules doesn't change anything. Everything's already linear. Okay. Right. And you can define dualizable objects in here. It's the same definition, you just forget the two morphisms and ask for, in the underlying symmetric monoidal category, you just ask for dualizable objects. Let me give some examples of dualizable objects. Dualizable DG categories. In fact, all the examples I wrote here are dualizable. And let me tell you how the duals look.
Yeah, I have a small question. Usual R models as so is as a category of just models, not DG models. Is it inside?
It's not an object here because it doesn't have all Hammond-Humpy limits and colimits.
Ah, okay.
Mm-hmm. Yeah. So all objects here automatically turn out to be what are called triangulated DG categories.
Mm-hmm.
So they're kind of far from abelian in general. Okay, so dualizable is just dualizable. There's nothing new to define. You just forget that you have two morphisms. But let's give some examples. So in the examples, what is the dual of R modules? Well, it must be something natural that you build from R. What could it possibly be? Yeah, it must be R op modules. Okay, and let's explain exactly how. Okay, so I need to tell you what the pairing is, for example. Okay, there was an additional property. So I should have said this here. Another nice property of this tensor product of DG categories is that if I tensor together two module categories, I get modules over the tensor product algebra. Okay. So now, if I tensor together R op and R mod, this is RE mod, RE being R op tensor R. It's the algebra whose modules are bimodules. And so the pairing, remember functors are given, continuous functors are given by bimodules. So I need to give you a bimodule. And I don't need to tell you what the action of Z is, there's only one, but I do need to tell you what the action of RE is. So I just have to give you a bimodule. And I take the diagonal bimodule. Okay, so that's going to be evaluation. And the co-evaluation is kind of similar. So the co-evaluation is supposed to go the other direction. But I'll tell you what it is after a twist, right? So after the twist and this, it's also given by a bimodule. It's the same, but kind of considered from the other side. So Z now acts on, RE acts on both the left and right of R.
Then that goes to simply R.
R, yes. Mm-hmm. Okay, and then there's something to check to show that these are evaluations and co-evaluations. This is how the duality works for DG modules. That's one example. Second example, let's do local systems. Kind of more geometrically. I mean, it is a category of DG modules by this theorem we stated, but let's say it more explicitly. So loc, I'm going to just write loc instead of loc infinity for now on, because we're cool kids. Right, so this was kind of an example one. Example two, well, another nice feature of this tensor product is that it behaves well with respect to the product of spaces. That's a kind of Kuhn theorem, if you like. You can think of local systems as a kind of categorical homology, and then this is the Kuhn theorem. The functor is kind of the one you think it is. So this thing is kind of roughly generated by pairs. And this goes to the Brav product. Okay. So now here's what we do. Claim is that loc x is self-dual. That's something special about the kind of geometric or topological situation. R op is usually not isomorphic to R. So R mod is not usually self-dual.
Yeah, but for the group algebra,
they are, yeah. For a group algebra, they are, but then it's a specific isomorphism. Little g goes to g inverse, right? So what is this? How do I do this? I have to give you the pairing between loc x and itself as well as the copairing. So the pairing uses this equivalence. It pulls back along the diagonal. And then takes homology with coefficients. So if P is the map to point, this is the take homology functor. Chains. And that it has to be homology in general, not cohomology, because it's supposed to be dualizable in this category where the functors are continuous. And in general, taking cohomology is not continuous. This is one reason homology is kind of more natural for this situation. And the other, so that's the pairing. And the copairing.
But I forgot gamology or the
Homology.
C star looks like tensor with dualization shift, something like that. Or
It was tensoring with the, in terms of algebra, it was tensoring with the trivial module. Remember, it was kind of group homology. And because it's tensoring, it's a left adjoint, and so it preserves colimits. And cohomology was given by humming out of something. And that doesn't typically preserve colimits, unless you're lucky.
Yeah, I really don't understand. So you say that in definition of gamology there is no shifting. I just don't understand what's the difference between tensoring with something trivial and con taking with tensoring with constant shift and taking holds.
Well, let's do an example. So for instance, RP infinity is B Z mod 2. Yeah. So homology is group homology. Cohomology is group cohomology. Right? So I need to resolve Z mod 2 over itself. This is some infinite periodic thing. And if I hum out of that, out of something very big, into some infinite direct sum, there's no reason for the image to be kind of finite.
Yeah, maybe I don't understand this at the level of shifts. So I understand that the group homology are not the same as group cohomology, but I trying to recall myself the definition of C star in terms of shifts.
So there was this, as Alexei said, you could take a kind of compactly supported, what was it? Something like compactly supported cohomology after tensoring with the dualizing sheaf, something like this. But then to apply to this kind of example, I would need some, I guess I could take the cellular model of RP infinity. Is this even, yeah, that might work. But so I think this functor of homology, I don't like to describe it in terms of sheaves. I think of it as a more homotopical thing. It is really just a left adjoint, and what it really is, remember I said that you can think of a local system as a representation of the infinity groupoid. So I have a functor from the infinity groupoid to DG modules, and I take the colimit over that. That's what homology is.
Actually, I comfort with definition with compactly supported sections. So
Okay.
I see that.
Actually, compactly supported is good also, because that also is continuous. Sections is not, but compactly supported sections is. Okay. So the co-evaluation is pull back, which means take the constant local system, pull back from a point. And then take this kind of compactly supported push forward, if you like. Okay, so what is this? This is co-evaluation. So these are our two basic examples. QCO works very similarly. Sheaves also works similarly. You have to take compactly supported push forward instead of push forward. Very good. Hi. Okay, so now note. Let's say in a symmetric monodal 2 category, when I take endomorphisms of the unit, remember a 2 category had objects, morphisms, and 2 morphisms. If I fix an object and look at its endomorphisms, that's like a set of objects, but then I have the 2 morphisms between the 1 morphisms. So the endomorphisms of any object again forms a category. So it's a category, not just a set. So the objects now are the endomorphisms. The morphisms are the 2 morphisms. So for instance, in the 2 category of categories, if I fix a category, I can look at its endomorphism category, whose objects are the functors from the category to itself, and whose morphisms are the natural transformations. And so, so that means if I have a dualizable object in a symmetric monodal 2 category, then and an endomorphism, then trace a phi lives in endomorphisms of the unit. This is an object. So in the 1 categorical setting, this is a set. You just get a point in that set. Here we get an object in a category. Right. And special case, of course, would be phi is the identity. Okay. So I want to compute this in a few cases. So let's do examples. So, well, actually, let me give a definition. So, given a dualizable DG category, for instance, DG modules or local systems, its Hochschild chains is, let me say it like this. So it's going to be trace of identity on D, but thought of as a Z module, or K module if you have some ground commutative ring. How do I think of this as a Z module? This is endomorphisms, continuous endomorphisms of Z modules. Remember, this is the unit for this tensor product of DG categories. And remember, how did I give a functor between module categories? I just gave you a bimodule. But a bimodule over Z is just a complex of abelian groups. So these are equivalent. So let's write out what it is explicitly. Just remember what the trace is. It's I have Z modules. I have this co-evaluation. If I had some non-trivial thing, phi, I'd have to put it in here, but I don't. And then evaluation. And so this continuous functor is determined by what it does to Z, and by definition, it's this thing. So I'm going to write this as it's just the image under this. And let's see that that agrees in the case of an algebra. Let's see that it agrees with the definition that we had last time. This seems like a ridiculously abstract way to get something which is, for an algebra, just given by some explicit complex. But it's very good for functoriality, and it's very good for comparing Hochschild homology of different categories, of different origins. Okay, so example. Let's suppose D is DGR modules. Then let's compute this trace. So I have composite of these two things. So one, remember the co-evaluation, evaluation were both given by the diagonal bimodule, but in different ways. So here, this was supposed to be R, where RE acted on what? On which side? I think. So here, this should be RE acts on the right, and this should be RE acts on the left. So what's the composite? I didn't say this. How do you compose bimodules? You take their tensor product. So this will be Z goes to the diagonal bimodule where RE acts on the left. And then this will send it to the tensor product, like this. And because we're cool kids, we're not explicitly writing the derived tensor product. Okay? And that's exactly Hochschild chains. Right? It was the tensor product of the diagonal bimodule with itself. So it agrees, this abstract definition agrees with the more classical definition in this example. Let's also do this for local systems. So now we're going to see how to compute the Hochschild homology of local systems. That's also good. In fact, that might just be the end of the talk. That's the theorem, right? Right. So I think I can. So we'll use some kind of basic functoriality and facts that I didn't mention. I'll just mention them in the proof. they shouldn't be too surprising. So here's the theorem. Hold on. Hold on. Maybe I did forget to introduce something. Maybe it's enough. So I'm ignoring the circle action because that's more subtle. I'll say something about it when we're done. So theorem, Good-William-Jones. The proof is a bit different. A Hochschild homology of the category of infinity local systems is naturally isomorphic to homology of the free loop space. And this is also compatible with circle actions, but it requires more work to set that up. So the proof is the following. Let's try to compute the left-hand side. So I'm going to do it as follows. I'm going to draw a diagram. So I have P mapping, X mapping to point. I have the diagonal. I have the diagonal. And I have the point. And remember how the duality worked for local systems. The coevaluation was pull back and Schrieg push forward, and the evaluation was pull back and Schrieg push forward. Okay. And let's note one more thing. The homotopy pullback here is the free loop space. For instance, if I resolve this by a path vibration.
Sorry, you might have mentioned this, but the push forward is, does the push forward preserve the category of shapes
Yes, because it's not exactly push forward as sheaves. It's just the left adjoint to pull back. And so if you want to compute it, like in an explicit model, you have to resolve your map by a vibration and then take like compactly supported push forward, something like this. But it exists for formal reasons as the left adjoint of the pullback. And it can be computed by some colimit formula. Some fancy homotopy colimit formula shows that it exists.
But do other push forwards exist?
The usual push forward, the star push forward, certainly exists, and that's easy. You don't need anything fancy to show that exists. You just kind of write it down.
Yes, but which maps are we allowed to?
This is all homotopy invariant.
For example, if I take any.
So if you try to model them as sheaves, then you start asking questions like this. If you take this homotopy invariant version that I mentioned in terms of the infinity groupoid, then all these are just left and right Kahn extensions. And so that you don't have to worry about this. So So pullback just is pullback. It's just restriction, and then that has left and right adjoints given by left and right Kahn extension.
Yes, but well, I'm interested in what happens for sheaves of the type we started with.
I don't know. I mean, I don't think that the left adjoint, I think, doesn't exist in general for all sheaves.
Well, for sheaves, which complexes of sheaves with locally constant.
It happens to, but I don't know necessarily that it admits a kind of topological interpretation. It's a kind of purely homotopical construction. So I think to compute it, you would have to replace your map by a vibration and then hope that it's nice enough that it makes sense to talk about compactly supported push forward, and then maybe you have to stick a dualizing complex in there, as you said. I don't know. I'm not sure, but in this purely homotopical setting, it's a left Kahn extension. Okay, so right. So I don't need this yet. This will appear when I appear here. I'm just completing the diagram. Okay. So I know that by definition of this Hochschild chains of a DG category, a dualizable DG category, this is pullback of Z, shriek push forward along the diagonal, star pullback along the diagonal, shriek push forward. So by definition, we have this. Well, it's not exactly a definition, it's by definition and the fact that I told you how to identify local systems with its own dual. So this is by definition and self-duality. There are other ways to identify it with its dual. You could like twist the identification I gave with an autoequivalence, but with respect to this identification, this is what we get. Very good. And now we have a kind of push-pull in the middle here. And there's a base change formula for these. So fact shriek push forward and star pullback satisfy base change. In particular, so let me give these maps names. Let's call this pi. In particular, I have, if this is star, star is the other way around. So like this. And now look at what this thing is. I pulled all the way back up to the free loop space, so I get the constant sheaf on the free loop space. And then I shriek push forward all the way to a point, which is homology. Okay. So this is, this part here is just constant sheaf on the free loop space. And this part right here is just chains. Okay, which is what we wanted. This is what I meant by homology, the chains. Okay, so the proof is define Hochschild homology of G categories via a trace. Identify local systems with its own dual so that I can actually compute it in this way. and then use this base change for homotopy pullbacks for local systems. And so I give you a list of properties that have to be true in order for this argument to work. And then one has to justify these properties. So all of this stuff can be found in these formal properties, not this particular application. Can be found, there are various places. One place is in this book, Higher Algebra by Lurie, but this book is hard to read. Another place is Papers of Akil Matthew, who was a student of Lurie. So he's written a lot of, his first few papers, I think, were about these categories of local systems. Oh, you know what's easier to read than Lurie's books are his lecture notes. So there's a course of Lurie on, I think it's L theory in surgery. So there's stuff in there about local systems and constructible sheaves. And it has most of this formalism in it, including probably the base change formula. If not, the base change formula is in Lurie's paper on rational homotopy theory. So that's the argument. You could ask, how do I get the circle actions compatible? And this can also be done, but it's a little fancier. So it turns out to be true that the trace of identity in this setting always has a circle action on it. And there are two proofs of this. One involves something that kind of generalizes the Hochschild complex. It's not called the cyclic bar construction. The other uses the one-dimensional cobordism hypothesis, which is easier than the two-dimensional cobordism hypothesis, but still not so easy. So one way or the other, there's a circle action on trace of the identity. And it turns out you can also, in a certain category, interpret the loop space as a trace of the identity. So maybe this is worth mentioning. And this is close to your category of correspondences that you talked about. So what time is it?
Well, it's 7.
Okay. Do you want me to say anything more, or should we stop? How
I have a question.
Mm-hmm.
Do you need to catch a train?
I think I am not going to catch a train. Let me check. I will not catch the next train, so I'm free until like 8. I have another hour free. But I want to eat.
So again, the statement of Goodwill-Jones applied to any topological space.
Yeah, any homotopy type.
So maybe I don't understand again how gamology appears here through just taking compounding supported push forward because
It's not in general. Maybe doesn't emit this description because you might not have.
Okay. So you abstractly define it as adjoint.
Yes, as left adjoint a pullback.
Okay.
And then you can do a little better than that. You can say that it is the homotopy colimit of a certain kind of homotopy diagram. So there's kind of an abstract formula for computing it.
Yeah.
And this is how you know it exists, because it can be given as some homotopy colimit.
Yeah, I mean, it sounds like a miracle. For example, I have log x mapped into log of point,
Mm-hmm.
and I just don't understand how without the realizable shift you obtain that gamology are dual to cohomology. I mean, a C with bottom star and C with upper star.
If these adjoints exist, then it's clear, yes?
Yeah.
So you're asking why do these adjoints exist? And then this is not so clear from the point of view of sheaves, like all sheaves. It is more or less clear from the point of view of this DG algebra. Because suppose I have an augmented DG algebra like this. Then I have a restriction along epsilon. Okay, and the restriction has two adjoints given by tensoring with this or homming out of it. So from that point of view, it's clear. You could ask, what does it have to do with homology or cohomology? And I think probably the best way to prove that this is homology actually is to check that it satisfies the Eilenberg-Steenrod axioms. So if you know that it's given by some colimit formula, it preserves homotopy colimits. Like colimits commute with colimits. And then you compute what it does on a point, and then you're done.
Yeah, but again, if we recall the statement of the existence of functor between log infinity and this model, we say that gamology are given exactly by tensoring with just this. Is that right?
I can give an independent definition in terms of these representations of an infinity groupoid.
Yeah, maybe my question is the following. So maybe I get that monoidal structure in log infinity does not come from monoidal structure of sheaves.
Yeah, it has to do with the Hopf algebra structure on this.
So it's tensor product is really.
No, I mean, I think it is the case that I think this inclusion is a tensor functor.
But again, this tensor product in log infinity is not computable by taking tensor product in ambient category of sheaves, right?
No, I thought it was.
Because
Is it not? I think it is.
if it is, then okay, you are obtained for free description of gamology without dualizable.
No, because this is tensor over R, not just. This is not tensor with a constant sheaf.
Yeah, but in description, we have a functor between log infinity and setting, and okay. This is not a constant shift. This
Is the constant module.
Right.
Yeah.
And in terms of shifts, this is this should be.
It's not given by tensoring with a sheaf, because that would take you from sheaves to sheaves. It's tensored with a bimodule. No, it is what it is.
miracle? Because there is something you tensor with, but it not come from.
But it's not just tensor width in the tensor category. It's this kind of relative tensor product over. Look, it's tensor over R. It's
Okay. So maybe I reformulate the question. It is not true that this pointer is realizable in terms of shifts as tensoring with some shift and then taking global sections or compactly supported sections.
in some cases it will be.
If there is a realization object.
Yeah.
But if not,
Then if not, it just is what it is. Yeah, it's some. It can be computed algebraically like this, or homotopically as some kind of homotopy colimit.
Okay, so really this base change formula should be something tricky.
It's pretty formal. So the proof that I've seen is in Luri's rational homotopy theory paper. He does the cohomology version, so for the star pullback, but that formally implies the one that I wrote down by some adjunction. And he does it pretty explicitly in terms of Kong complexes. So I try to remember. So there, by adjunction, there's a comparison, and you're trying to check that this comparison is an equivalence. I guess if you know, since everything, the way I've written it, everything's continuous, commutes with colimits, and because the categories are generated under colimits by very simple objects, I told you what the generators were, it's probably enough to check this on the generator, but I don't know if that makes it any easier. Luri's reduction is something else. I don't remember. It's not a very long argument, though. It's not that hard. No. But there's at least just by adjunction a comparison, you have somehow to check that it's always an isomorphism. Okay. I think it's enough.
Thanks.